acceleration is the rate at which velocity changes with time. That's our definition, so you'll want to write that down. Acceleration is the rate at which velocity changes with time. So, velocity can change when an object, when the speed of the object changes or when the direction of the object changes. So if we think back to the last chapter, velocity is not just a magnitude, but it also has a direction. So if your speed changes or your direction changes, then you have a change in velocity. And the rate at which that change takes place is what we call the acceleration. So acceleration occurs when there is a change in speed, a change in direction, or both. Okay? So acceleration can occur when there's a change in speed or a change in direction or both. Now, generally, we think of acceleration as being something positive. So if you think about your everyday language and how you use this word, usually think about accelerating when you're putting your foot on the gas. You're driving your car, you put your foot on the gas, you say you are accelerating. That is true. But if you take your foot off the gas, then you are also accelerating because you are still changing your speed. Or if you turn around and go the opposite direction, that's acceleration because you're changing your direction. The term we tend to use when we're slowing down is deceleration. So it would be like acceleration with a negative sign in front of it. Okay? So let's move on. Bless you. So here's an example. A cyclist accelerates by increasing his speed 2 meters per second every single second. So after the first second, he's going 2 meters per second. After the second, he's going 4 meters per second. So after the third second, he would be going how fast? 8 meters per second. Yeah. So every second, he's getting 2 meters per second faster. Okay? That's what we mean by acceleration. So you can see in the little graphic, here's 0. So both his time and his velocity are 0 because he's literally not moving. And then after 1 second, his velocity is 2 meters per second. And so you can see that arrow indicating his speed or his velocity. Then at 2 seconds, he's going 4 meters per second. Okay. 3 seconds, he's going, I said 8, it should be 6. Sorry. 3 seconds, he's going 6 meters per second. And you can look down here and see what distance he's covered in that time. Okay. All right. And this is just kind of a practical application that I've always thought was kind of neat. Humans can't detect constant velocity because because it's constant, but we can sense acceleration. So we may not be able to tell that somebody is going a velocity of 5 meters per second, but we can tell when they speed up or when they slow down. We can tell that by, if we're speeding up, we tend to feel the seat pushing against us, pushing us forward. So, when you slam your foot on the gas and you take off, you feel that. You feel that seat at the back feels like it's pushing you forward. Or if you slam on your brakes and you feel that seat belt pushing you back. And this is one that was always fun as a kid. If you're in the back seat of your parents' car and they go around a curve really fast and slings you one way and then it slings you the other way, or it feels like it is. Maybe it's not literally slinging you, but you tend to lean to one side or the other when you're going around that curve. That is our body's way of sensing acceleration. Okay, so equations. Need to make sure we write these down. There's going to be more of them in this chapter. We're going to kind of keep building. So the first one is we need to know how to determine average velocity. Average velocity of an object is a change in its velocity divided by a change in time. So that, remember, that change in is just the little delta sign, and it's always final minus initial. So change in velocity divided by change in time. That is average acceleration. So that's the first of our equations for acceleration. Got that down? Almost? Almost. Okay. So the units or the dimensions of average acceleration are meters per second, or we say meters per second squared. That's how we write it, and that's how we say it. So that is our unit of acceleration, meters per second squared. Because it's velocity, which is meters per second, divided by time, which is seconds. So it turns out to be meters per second squared. So make sure you know that unit. As I said, knowing your units and knowing what the units should come out to be when you put it into an equation is going to help you understand whether or not you got your problem right. So there's just some typical accelerations, and they're all measured in meters per second squared. This one's interesting. Acceleration required to deploy airbags, 60 meters per second. It's pretty fast. When they deploy and come out, the speed at which those things deploy is extremely fast. Obviously, it would have to be in order to protect you. The problem with that can be for children in the front seat, which is why it always says, do not put children in the front seat. Because when that airbag deploys, they are not big enough, their bones are not solid enough to withstand that deployment of that airbag in their face, and it can cause a lot of damage or even death. And that's why they say don't put a kid, even in a car seat, don't put them in the front seat, because even in that car seat, with that airbag deployed, it's going to push that car seat backwards, and it can cause all kinds of damage there too. So kids have to go in the back seat. I think is until they're 12, I believe. I think it's 12 or 13. Yeah, 12, I believe. So, and my kids were always very tall. You see a picture of my husband. They were always very tall. So they always wanted to sit in the front seat because they were tall, and they were, because they were tall, they had more mass than most children their age. So we were like, yeah, we can put them in the front seat. My dad, who was a pediatrician, he was like, no, you can't. Like, why not? Look how big they are. Bones aren't solid yet. No matter how big they are, their bones are not completely solidified until they reach a certain age, and until they said, even though they weigh a certain amount or they're a certain height, keep them in the back seat as long as possible. So I was like, okay, I will. It made sense after he explained it, but okay. Let's look. So here's another example. The speed of an object increases when its velocity and acceleration are in the same direction, but decreases when the velocity and acceleration are in opposite directions. So you want to jot that that down. That's going to help you as far as when you're rationalizing problems. So if your velocity and your acceleration are in the same direction, then your speed is going to increase. So if we look at this guy, he's accelerating in the forward direction. His velocity is in the same direction. Then his speed is going to increase. Okay? This would be what would be happening if you put your foot on the gas. If you're at a stop sign, you put your foot on the gas and you take off. Well, obviously you're going in the same direction and your foot is on that gas, so you're accelerating and you're going in that same direction and your speed increases. That's why you see your speedometer go from 0 to hopefully not over the speed limit. But anyway. And the opposite happens, so your speed is going to decrease if your velocity and acceleration are in opposite directions. So again, this is what happens when you put your foot on the brake. Okay, when you're supposedly coming to a stop at a stop sign or a red light, you're putting your foot on the brake, so your acceleration is going in the opposite direction because you're putting your foot off the gas and on the brake, or at least off the gas. But you're still going in the forward direction. So your acceleration is going in one way, your velocity is going the other way, which means your speed is slowing down. So that's why you'll see that speedometer drop down. Okay? So, and here's a graph of these two things. You might want to jot this graph down because we like to look at graphs. If we plot velocity versus time, if we have a positive slope like you do right here, this would be where acceleration is increasing as well as velocity. So then our speed increases. So we're speeding up in that situation. If you look at the second line, okay, we have our velocity is going in one direction while our acceleration is going in the other direction. So we are slowing down. That has a negative slope to it. Okay. So we all have that down, able to recognize that. All right.